Okay, Le Chatelier's principle. Okay, here it is. This will be a little confusing at first, but hang in there. If a change is imposed on a system at equilibrium, the reaction will shift in the direction that tends to reduce that change. So when we look at a reversible reaction, the term shift has two meanings, either shifting right, in which case you make more products, or the reaction shifts left, in which case you make more reactants. So this is going to be a case where the reaction is at equilibrium, but we can impose changes on the equilibrium to cause the reaction to shift in one direction or the other. So it's kind of messing with an equilibrium system. Two connected water tanks is a good analogy for this. Okay, so here we have two water tanks, and of course they're level by the force of gravity pulling down on them. Okay, so we're going to be adding and taking away water, and what we want to do here is treat the tank on the left as the reactants, and on the right is the products, and the shift would be the movement of the water from one side to another. So what we're going to be doing is adding and taking away water from the tanks. So again, the analogy here is think of the tank on the left as the reactants, on the right as the products. Okay, so here, first, add water.
When we add water to the tank on the left, the water in the tank on the right moves up, and that on the left moves down. The water moves from left to right, so we say that equilibrium shifts to the right, as it would if we added more reactants to a reversible chemical system.
Okay, so we added water to the left side. And so this is Le Chatelier's principle in action. We added water to the left, so what will happen is the reaction will shift so that we make more water on the right, or of course we're talking about products. So if we add more reactants, we'll end up making more products. The reaction will shift to the right. Now let's try adding water on the right side.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
Okay, so if we add water to the right side, the water will move over to the left, just like if we added more products, we would end up making more reactants. The reaction would shift to the left. So another way of thinking of Le Chatelier's principle is whatever you do to the system will do the opposite. So I added more water on the right, so we're going to make more water on the left. If I added more water on the left, I'll make more water on the right. Okay, now let's look at what happens if we take away something.
Removing water from the left tank causes water to move from the right tank to the left. Equilibrium shifts to the left, as it does in a reversible chemical system when we reduce the quantity of the reactants.
So if we remove water from the left side, water will come to replace it. So if we remove a reactant, the reaction will shift to the left to make more reactants.
Removing water from the right tank lowers the water level of the left tank as water moves from left to right to regain an equilibrium. The equilibrium shifts to the right, as it would in a reversible chemical reaction if we subtracted product from the system.
So we remove water from the right, be like removing a product, so the reaction will shift to the right, just like the water shifts to the right. So let me kind of recap this. If I add a reactant, I'll make more products. If I add more products, I'll make more reactants. If I remove reactants, I'll make more reactants. If I remove products, I'll make more products. And the shifting just refers to that. So if we say something shifts right, for whatever reason, we're making more products. If something shifts left, for whatever reason, we're making more reactants. The primary factors that can shift an equilibrium system are concentration, temperature, and pressure. Now, pressure is for gases only. Pressure does not affect liquids or solids. or aqueous solutions. Okay, here's a little introduction to this, and then we'll look at some examples.
Le Chatelier's principle states that a system in equilibrium that is subjected to a stress will react in a way that relieves the stress. Some of these stresses include changes in pressure, changes in concentration, and changes in temperature. Consider this reaction of nitrogen and hydrogen to form ammonia. A change in pressure affects only equilibrium systems in which gases are involved. If the pressure of a system is increased, the equilibrium will shift to favor the reaction that produces the fewest moles of gas. This action will reduce the total pressure of the system. In this example, more ammonia is produced to reduce the pressure on the system. A change in the concentration of one of the reagents also affects a system. If the concentration of one of the reagents is increased, the equilibrium will shift to favor the reaction that reduces the concentration of the added reagent. If more hydrogen is added to this flask, more ammonia will form to reduce the hydrogen concentration. A change in the temperature of a system can also stress a system. Reversible reactions are exothermic in one direction and endothermic in the other. According to Le Chatelier's principle, the addition of heat shifts the equilibrium so that the reaction that absorbs heat is favored. If heat is added to an endothermic reaction, the equilibrium shifts to favor the formation of the products. If heat is added to an exothermic reaction like this one, the equilibrium shifts to favor the formation of the reactants.
Okay, so we will be looking at this very reaction, the synthesis of ammonia, called the Haber process. Okay, so this is the Haber process, nitrogen plus hydrogen to give us ammonia. Now this is an exothermic reaction. Okay, now we're going to be looking at how changing concentration, changing temperature, and changing pressure affects this equilibrium system. So in other words, by imposing a change, will it shift to the right or shift to the left? Okay, now one thing that is important for you to understand, when we look at a chemical reaction like this, it's easy to kind of segregate it. So have the reactants on the left side, the products on the right side, like they're two different worlds almost. But in fact, they're all taking place, the reactants and the products are all taking place within some sort of container. Now, I wasn't able to find an animation that had 3 different colors because you have 2 reactants and a product, so it doesn't really matter. But the reactants and the products all are in the same container. And so when we say that a reaction shifts to the right or to the left, it doesn't mean that they leave the room or something. It's just that in the container, you have more. If it shifts to the right, you would have more ammonia. If it shifts to the left in that container, you would have more nitrogen and hydrogen. All right, so let's first look at changing concentrations. So now changing concentrations means that we're going to be adding more moles per volume. So if this was our volume and we added more of a gas to it, we would be increasing the concentration. If we removed some of the gas, we would be decreasing the concentration. So let's look at the change. So if we add hydrogen, well, hydrogen is a reactant. So Le Chatelier's principle says if we add a reactant, the reaction will shift to counter that change. So in other words, it'll shift to the shift to the right, make more products. If we add ammonia, ammonia is a product. So the reaction is going to shift to the left. If we remove nitrogen, well, nitrogen is a reactant, so if we remove it, well, the reaction is going to shift to the left to counter that change. So by shifting to the left, it's going to make more nitrogen. So again, the Chatelier's principle is just like whatever you do to the reaction, it's going to counter that effect. If you remove something, it'll replace it. If you add something, it's going to remove it. So if I remove ammonia, it's going to shift to the right. Remove ammonia, shift to the right. Okay, now let's look at changing temperature. Okay, now this is going to be very dependent upon whether the reaction is endothermic or exothermic. And for this reaction, this is an exothermic reaction. So remember, if it's exothermic, That means that heat is a product. That's one of the things he did in the last unit was rewrite the energy within the equation itself. Remember that? Well, this is exothermic, so we could say that the product is 2 moles of ammonia and 92 kilojoules of energy. All right, so let's look at the change here. If we increase the temperature, well, if we increase the temperature, how do we do that? We do that by adding heat. So if we're adding heat, we're adding a product because the heat is a product. So if we add a product, it's going to shift to the left. If we decrease the temperature, so that means that we're going to be removing heat. So if the reaction is taking place in this vessel and we cool it off, well, what's happening is we're removing heat. And if we're removing heat, it would be just like removing ammonia. We're removing a product. So it's going to shift to the right. See how that works? Okay, now again, this was for an exothermic reaction. The opposite would be true if it was an endothermic reaction. If it was an endothermic reaction, then heat would be on the reactant side, and these temperature changes would cause the opposite shift. Okay, now let's look at pressure. Okay, the key idea when we're dealing with pressure is that the more moles of a gas that you have, the higher the pressure will be. So when we look at the pressure again will only be a factor for gaseous reactions, which is the case that we have here. Everything's a gas. So what we need to do is to look on the reactant side and the product side and see which side has more moles of gas. Well, for this reaction, we have 4 moles of gas on the reactant side. We have 1 mole of nitrogen and 3 moles of hydrogen. So there's more moles on the reactant side than on the product side. The product side, there's only 2 moles. So if we increase the pressure, and the easiest way to think of that is by decreasing the volume. So imagine if I was to squeeze this container into a smaller volume, but still have the same number of particles, well, the pressure would increase. Just like if you were to take a balloon and squeeze it, the pressure is going to increase. So in order to counter that change, we want to have it shift so that we have fewer moles. So if we increase the pressure, the reaction is going to shift to the side that has the fewer moles. So it'll shift to the right, fewer moles of the gas. And if we decrease the pressure, we can do that by expanding the container, increasing the volume, then the reaction is going to shift to the left, so we have more moles on the left side, so that would increase the pressure. So let me kind of recap this. Increasing the pressure by decreasing the volume, the reaction is going to shift to the side that has fewer number of moles. That will decrease the pressure. So you increase the pressure, it'll shift to the side to decrease the pressure. If you decrease the pressure, it'll shift to the side to increase the pressure. Okay. Okay, hence for an equilibrium system, treat heat as you would any other reactant or product. So that's just like what I just talked about. Only closed systems will reach equilibrium. That is, reactants and products cannot leave the reacting vessel. For example, one of the reactions we've talked about recently was when you put magnesium into hydrochloric acid and a gas escapes the beaker. Well, that couldn't be an equilibrium system because you have one of the products is leaving. So it's not going to be able to be reversible because it's no longer around. So it has to be a closed container, or the reaction has to take place within solution or within a sealed container. And last, and this is kind of out of left field here, a catalyst has no effect on equilibrium. It only increases the rate at which equilibrium is reached. Okay, now I'm going to show you a summary video. It's a really nice little video. It's just a couple of minutes long. He's going to go into a couple of things that we haven't talked about yet, but we will. I might show you this video again next week or at the end of this week.
Systems in dynamic equilibrium are very sensitive to changes in concentration, pressure, and temperature. Le Chatelier's principle enables us to predict the effect of these changes. It states that if a system in dynamic equilibrium is disturbed, the equilibrium position shifts to counteract the disturbance. For example, if more reactants are added, the system removes them by creating more products. If products are removed, the system replaces them by converting reactants. Consider the Haber process, in which nitrogen and hydrogen react to form ammonia. Le Chatelier's principle tells us that if the pressure on the system increases, the equilibrium position shifts to the side where there are fewer moles of gas, and hence a lower pressure. The forward reaction is exothermic. Energy is released when ammonia is formed. Increasing the temperature drives the equilibrium position to the endothermic left-hand side, as the system absorbs additional heat energy from the surroundings. Decreasing the temperature drives the equilibrium position towards the exothermic right-hand side. The system gives heat energy back to the surroundings. A better yield is obtained at lower temperatures, but this benefit is offset by a slower reaction. Industrially, a temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and an iron catalyst is used.
Okay, we'll actually talk about that, the industrial processes of the Haber process and another one called the contact process. But for now, boys and girls, that is the end of notes.